Hey, welcome back. Today we're going to be talking about how to solve mass flow rate problems, specifically momentum problems, for AP Physics C mechanics. So you may have not heard of these before, but this is a subset of linear momentum problem that you're going to need to know how to do if you're an AP Physics C mechanics student. So in the problem itself, you've got a bucket, you've got some water coming out of a faucet, and there are three forces pushing down on a scale. So the scale is that rectangular gray thing right there. So there's the weight of the water, there is the weight of the container, and there's the force of the water as it's coming down, entering into the other container of the water and pushing down on the scale. Now the scale has to overcome all of those things, so it's going to have a pushback. And so we can immediately start to think about what are our forces involved here. So let's just set up what I would call the sum of the forces strategy and think to ourselves, what's happening with the forces here? So we would say the sum of the forces in the y-axis, and we just add things up. Let's assume up is positive and down is negative. So we could say we have the force of the scale minus the weight of the water minus the weight of the container minus the force of the water. The force that the water coming down and hitting the other water is actually applying on the scale itself. So the scale has to overcome all of that, right? And we could say the sum of the forces in the y is equal to mass times acceleration of the y. We can think of this as like the scale, for instance. The scale is not moving. Since it's not moving, its acceleration of the y is 0. That means we can set these things equal to each other, and effectively we have proven that the force on the scale, it's going to have to overcome all of these things, these three other factors. It's going to have to overcome the weight of the water, and it has to overcome the weight of the container, and it has to overcome this force from the water falling. The water is falling, and then it interacts with the other water, and that's putting a force on the scale itself. So that scale has to overcome all three of those things. Let's see what we know from the problem itself. So it says water of density 1,000 kilograms per meter cubed. Okay, so 1,000 kilograms per meter cubed. This is one way to think about our density here. Falls without splashing at a rate of 0.333 liters per second. We'll call this a flow rate. And think about it, that's in terms of volume per seconds. Now there is a handy thing that we can talk about with water, and that is 1 kilogram of water is equal to 1 liter of water. And so if that's the case, we can write a mass flow rate here of 0.333 kilograms per second. And conceptually that's what we mean by a mass flow rate. That can help you to understand what we're talking about, how much mass is flowing, and it just works out that water is really easy to work with by design in terms of our units. Okay, so what else do we know here? It says it falls from a height of 44.4. Now that is definitely not the scale, right? We're saying this is 44.4. That's hard to believe. Yes, I agree with you on that. It's just written with a very large number so that the actual numbers work out, and so I'm going to rewrite that in a way that's a little prettier to watch. So as this falls, this is really a conservation of energy issue, right? So you could say mechanical energy initial is equal to mechanical energy final, and you could say your potential initial plus your kinetic initial is equal to your potential final plus kinetic final. I could use U for potential like AP typically does, but I think you know what I'm talking about here. If we assume the water starts from rest, there's no kinetic here. I could also use capital K for kinetic. What I'm getting at though is we can get rid of these terms and think of this height difference as a conservation of energy issue. So you could say mgh is equal to 1/2 mv squared, and what we really want is we want the speed at which the water that's coming out of the faucet is going to hit the water level that we have here. That's what we're getting, is the speed value. We can eliminate these masses and we can say this reduces to 2gh. We need the root of that is going to be the speed at which the water hits the other water, so to speak. And we'll need that speed later. So that is why they give us this 44.4 meters, or I have a variant of it here, but in any case, We do have also the mass of the bucket. That's actually pretty easy, right? We need the mass of the bucket or the container. So the weight of that is just going to be mass of the bucket or mass of the container times gravitational acceleration. That's what we mean by the weight of the container here. And it says that the bucket is originally empty. What does the scale read at 1.23 seconds after the first drop contacts the bucket? So this problem, at first glance, if you've never seen a problem like this is going to be confusing, but I'm going to talk you through how to reason through this. So we've said in the past that the derivative of momentum with respect to time is force. And let's tease that out a little bit. Let's think about what that actually means. So you could say force is derivative of mv. And I want you to think to yourself, what is constant? This is a really crucial question for what we're doing next. What is constant here? So what I mean by that is, in the past, what we've done is we've said, oh, well, force is equal to, now if our mass stays constant, we could say dv dt, and that actually makes a lot of sense because dv dt is just acceleration, right? So force is equal to mass times acceleration, of course, that's Newton's second law, and that's assuming that mass is constant. So if we assume we have constant mass, this is what we end up with. But what if we have a situation where the mass is not constant? That's what we have here. We also have this situation with rockets, because rockets will lose their fuel as they go throughout their trajectory. But that's what we have here. We don't have a constant mass. The mass is continually changing. What we have is a constant velocity. So we can take the derivative of momentum, but if we assume we have a constant velocity, then we're going to have a different equation to work with. So the different equation is going to look like this. So that's going to be our equation that we're working with. And in fact, it's also up here. So if you see this equation, we are assuming that we have a constant velocity. What does that mean? That means the water is basically hitting the other water at the same rate the entire time, but the mass of the water inside the container is continually changing, and we need to account for that. So that becomes a challenging problem. Okay, we already said though that we can solve for this v. This v right here, I will try to save myself some room, but show you where we're going with this. We have this v over here, so we could say this is the force of the water. That means the force at which the water hits the surface that we're dealing with. So let's see if we can sub in 2gh here, the root of that, times dm dt, and we actually have this dm dt. This is the mass flow rate. This is really crucial to understand what's going on. So we could say the force of the water is equal to the root of 2 times 9.81 meters per second squared, and I'm going to need some more room here, times a height of 44.4 meters. That's all under a root, times the flow rate. Well, the flow rate we said was 0.333 kilograms per second. And so that means that the force that the water is pushing against the scale is going to be 9.83 newtons. So we were able to solve the most difficult part of the problem here now. So let's take that 9.83 and think about what we now know. This is our master equation here. We essentially now know this, we know this, and the weight of the water, what we're going to need to do is use that flow rate concept again. So let me show you what I'm talking about in a dark green color. We know that we have 0.333 kilograms per second of water being added, but we also know that we're dealing with 1.23 seconds. If we multiply these two together, that's going to give us our mass of the water, and then all we would need to do is multiply by 9.81 meters per second squared, and that's going to give us the weight of the water. Okay, what I'm going to do is move this to the side and write this a little more clearly so we can see what we're seeing here. So the force of the scale is going to be equal to the weight of the water. What's the weight of the water? Well, we know the mass flow rate. This is going to be kilograms per second. And we know that the water is flowing for 1.23 seconds. Let's think about what this is going to give us. This will give us the mass of the water that flows during that time. We do need to multiply that by 9.81 meters per second squared. Alright, so that right there, my friends, is the weight of the water. Alright, so then what else do we have? Well, we've got the weight of the container. That's really easy. So we're just going to say plus the mass of the container. Well, that is 2.22 kilograms times 9.81 meters per second squared. And that is going to be the weight of the container. Okay, and the last force that's going to impact our scale is going to be the force of the water. And that's what we figured out down here, right here. So that's just going to be 9.83 newtons is going to be that additional force involved. So the sum of all of those forces will be the force on the scale. That is how you would approach one of these problems here. It's actually, I think, a really cool problem, and it's a challenging one to think about these concepts in slightly different ways than you've seen before. But that is exactly what you need to do as an AP Physics C mechanics student. You need to be exposed to this for sure, because you might have a mass flow rate problem, but you also need to be able to think and apply this in new and interesting ways. Notice at this point right here, I could draw that with a little white star or something like that. You actually just kind of have to think on your feet and think, well, I know what the flow rate is, and I know how fast it's flowing. Honestly, if you just look at your units, over here you've got seconds, over here you've got seconds, you know those are going to cancel, and that will give you kilograms over here. That's a good way to reason through. Like, I'm saying think on your feet, but also use units as you go to help you to spot what your next step is going to be and to be successful on the AP Physics C mechanics test. So I do want to say I've gone over lessons, video lessons for an entire year of physics, as well as most of the ideas for AP Physics C mechanics. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.